Hi everyone, my name is Danilo Francati and I'm going to present Arcula, a secure hierarchical deterministic wallet for multi-asset blockchains. This is a joint work with Adriano, Luzio and Giuseppe Ateniese. We're going to talk about cryptocurrencies and blockchain. So let's have an introduction. A blockchain is a sequence of blocks. These blocks contain transactions that are linked together, and each transaction have a particular structure. So, for example, the transaction contains the amount of coins, then it contains a locking script that usually identifies the current owner of the transaction, so it contains the public key of the owner. And then there is an unlock script that allows to spend the transaction. How? So when you create a new transaction, you need to include an unlock script that essentially contains the signature of the new transaction. And the secret key used is the secret key that corresponds to the public key containing the locking script of the previous transaction. So the money that you are spending. And naturally, since you are spending the money, in the new transaction, there is a new locking script with the public key of the new owner. So in this talk, we're going to talk about wallets. Usually wallets contains our money, but when you talk about a cryptographic world, now a crypto wallet is a piece of software that instead of containing the money, contains the public keys and the secret keys that we need in order to spend our cryptocurrencies. Specifically, we're going to talk a specific class that is called hierarchical cryptographic wallet. So now it's a wallet that is shared among different users. And these users are ordered according to a hierarchy. And the property is that the wallet allows to generate the secret keys and also the corresponding public keys according to the hierarchy. So, for example, here the root node can generate the secret key of the node number 2 by simply using its secret key and so on and so forth. So, for example, then 2 can generate the secret keys and the public keys of the user 5 and 6. So, besides this hierarchical property, the wallet must be secure. What does it mean? It means that children cannot pull their data in order to expose the secret key of the father. So basically, you cannot escalate your privileges. So you cannot leak a secret key of any ancestor and spend, for example, the coins. And as I said, there is this hierarchical property to go from secret keys to secret keys, and this procedure can be a secret key procedure, so can involve some secret informations. But in this talk, we also want an additional property that is called public derivation. So it's also possible to go from public keys to public keys according to the hierarchy, and this derivation all involves public information. So why we want this property? Because, for example, this wallet can be used by a company, and the company must be compliant to some regulations, financial regulations. And the public derivation allows, for example, the possibility to give to an auditor the public key of the root node, and the auditor can check basically the status of the company, the money, by generating all the public addresses according to the hierarchy of the company. And why must be a public key derivation? So only involves public key information because we don't want to expose the secret key to the auditor that can be malicious. So generic, we're going to see that it's very hard to have the security and the public derivation together. And to do it, let's take into account the wallet proposed by the Bitcoin Improvement Proposal 32. So here in this wallet, the secret key is an element X, the public key is an element G to the X. There is a secret key derivation. So, for example, the root node can generate the secret key of the child number 2, by shifting its secret key. So basically, you take the secret key of the root node and you add a hash of 2, where 2 is the identifier of the node. There is also a public key derivation. So a public key, according to the secret key derivation, must be of the form G to the X0 plus the hash of 2. This is the public key of the user 2. That is, this public key can be entirely computed by using public information, because you can just take the public key of the root node and multiply it by G to the hash of 2, where hash of 2 is a public, can be computed by without using any secret information, because 2 is just an alphanumeric string. What's the problem with this approach is that it's not secure. So there is a privilege escalation attack. So for example, in this case, the node 2, in order to expose the secret key of the father, the root node, the only thing they has to do is to remove the hash of 2 from the secret key. That is a public computable way. So there is also another version that is called the hardened version of the wallet. And now in the hash, we also include the secret key of the father. So the hash is not the hash of the identifier, but it's the hash of the secret key of the father concatenated with the identifier, in this case, too. In this way, we solve the privilege escalation attack because in order to perform the attack, you need to know the secret key of the father. That is precisely the key that you want to expose, and you cannot perform the attack. There is a secret key derivation because, I mean, now instead of the father, for example, the root, instead of hashing just the identifier, it also hashes secret key. But what's the problem now is that we are losing the public key derivation because at some point you need to compute the hash with input the secret key of the father, and this is a secret information, so the public key derivation is not public, involves secret information. So this gives you the idea that it's very hard to have both properties together because the public key derivation needs to relate the public keys by a public computable relation. But usually this relation also affects the secret key. And if the relation is public, it means that usually what you can do, you can invert the secret key in order to expose and retrieve the secret key of your father. In order to remove this problem, you need to make the relation secret. But now if the relation is secret, you lose public derivation because it involves a secret information. In this work, what we're gonna do is we're gonna tackle this problem. We define the security definition of the two properties that I just defined. And we are not going to see the formal definition in this presentation, but we're going to focus on Arcula, an hierarchical cryptographic wallet that is secure according to the definition, and is probably secure, works with any signature scheme, so it means that it can be used on several blockchains, and is based on a cryptographic tool that is called Hierarchical key assignment that is well studied in the literature. So what is an hierarchical key assignment? An hierarchical key assignment, again, is similar. There is a hierarchy, but now instead of generating hierarchically public keys and secret keys, what we do, we want to generate symmetric keys. So that, for example, here the root node is able to generate the symmetric key of the node number 2 and so on and so forth. There is a security definition that basically is the usual one. So children cannot pull the data in order to expose the secret key of an ancestor or the father. And moreover, it's even stronger because from the point of view of the child, the symmetric key of the father is indistinguishable from a random bit string. So how we build Arcula? This is a toy example with 2 nodes, only the root node and one child. One user, another user. So what we do, we first run the hierarchical key assignment to generate a symmetric key for every user. Now, as I said, this symmetric key is indistinguishable from random. So what you can do, you can use the symmetric key as random coins of a keygen generator, where the keygen is the keygen of a signature scheme. So you generate a signing key and a verification key for every user. We do a last step. So now, for every node that is not, for every user that is not the root node, we generate a certificate. And the certificate, the objective is to link together the identifier of the node, in this case 1, with the corresponding verification key that we have generated. How we do that is basically a signature and the signing key of the root node of these 2 values, so the verification key and identifier. So at the end of the day, we're gonna obtain these, let's say, values. But how we can use these values to have a valid public key and a valid secret key that allows us to spend money on our blockchain system. So let's see an example and let's take into account the Bitcoin Cash scenario. Usually in the Bitcoin Cash, the user has a single public key and a single secret key. The locking script is composed by basically contains the hash of the public key of the owner. And now the locking script contains 2 elements. One is the pre-image of the hash, so it's the public key of the owner again, and also you have to prove that you can spend that money. In how to do that, you need to forge a signature under the corresponding secret key of the new that signed the new transaction. So, but now we have Arcula. Arcula have different elements. We can see you have a certificate, a signing key, and a verification key. So how we can use Arcula in a real model, real world, so we can cache in this case. So now the lock script looks like this. It contains mainly two elements. So the index of the user, or the alphanumeric string that identifies it. So one. And the verification key of the root node. Why the verification key of the root node? Because the root node is the most privileged user in the wallet, and its verification key can be seen as the master public key of the wallet. So with the verification key, we identify the wallet, and then with the index, we identify a user in the wallet. Then there is an unlock script that contains 3 values. Let's see why. So there is a certificate. I remember that does the link between the identifier and the verification key. So the first thing that the unlock script together do is to check the certificate. How? We take the identifier in the lock script, the verification key that has been provided in the unlock script, and we verify the certificate using the verification key of the root node in the lock script. If the certificate is valid, now we know that, for example, user 1 has a verification key 1 that has been certified by the root node. And after that, we do the standard check that basically you need to provide a signature under the corresponding signing key of the new transaction, that basically we are proving that you know the signing key of the verification key that has been certified by the certificate, basically. So by doing a mapping, now the lock script contains 2 elements, the unlock script contains 3 elements, and now we can basically order this value to basically define what is a secret key and a public key in Arcula. A secret key is a type of element, the signing key, the verification key, and the certificate. This because it's what you need in order to provide an unlock script. The observation is that the certificate can be made public, because in order to complete the unlock script, you need to know the signing key. So it means at the end, the secret key is just 2 elements. And then there is a public key, there is an alphanumeric string, the index, for example, and the verification key of the root node. So basically, you can see that the public key is basically like an identity-based address. So there is the public key of the wallet, okay, but then there is an alphanumeric string that you can choose that can depend on the model, but can be, for example, the name of a company or the name of the user. So at the end of the day, you have Arcula that generates this type of keys according to the hierarchy. Again, the secret key of the node I is the pair signing key I and verification key I, and now the public key I is basically the index I and the verification key of the root. We have a secret key derivation according to the hierarchy, because basically every signing key and verification key is computed by using the symmetric key provided by the hierarchical assignment has randomness. And we can go from symmetric key to symmetric key, and the knowledge of the symmetric key implies the own knowledge of the secret key, basically now. So we have a secret key derivation for the secret keys. We also have a security against privilege escalation for 2 reasons. First of all, because a user cannot leak the symmetric key of an ancestor. And so it means that it cannot also leak the signing key and the verification key of that user. And also because the signature scheme that we use to do the certificates is unforgeable. So you cannot create, let's say, fake certificate and break the security of the keys of Arcula, or break the unlock script of the system, or forge the unlock script of the system. And also we have a public key derivation, because by just publishing the verification key of the root node, we can generate every public key, because the only thing that you have to do is to append the alphanumeric string, the identifier of the user. So this concludes my presentation. You can find more details in the conference version, or in the conference paper, or in the resources full version online. And thank you for your time.